Welcome to Fun Facts Online. An earth-shattering revelation has sent tremors through the world of volcanology. Scientists have unearthed a hidden fiery artery connecting two of Greece's most formidable volcanic giants, Santorini and Kolumbo. This isn't just a story about two volcanoes. It's a narrative that delves deep into the Earth's crust, rewriting textbooks and forcing us to reevaluate volcanic hazards in some of the most populated places on the planet. The Aegean Sea, a cradle of ancient civilizations, is also a crucible of immense geological power. It's home to the Hellenic volcanic arc, a 500-kilometer-long chain of volcanoes born from the slow-motion collision of tectonic plates. For millennia, the most famous and feared member of this arc has been Santorini. Santorini, officially Thera, is the stuff of legends. Its iconic, crescent-shaped caldera is the breathtaking remnant of one of the largest eruptions in human history. Around 1600 BCE, the Minoan eruption blew the original island apart, creating the caldera and triggering colossal tsunamis that contributed to the decline of the Minoan civilization. But Santorini's story didn't end there. Over the centuries, new eruptions within the flooded caldera created the Kameni Islands in the center of the bay, with the most recent eruption occurring in 1950. Despite its quiet periods, Santorini has always been considered an active and potent threat. But just 7 kilometers away, hidden beneath the sea, lies another giant, Kolumbo. Kolumbo is a large, active submarine volcano. For centuries, its existence was only known from the catastrophe it caused in 1650. In the summer of that year, the sea began to bubble, change color, and grow hot. Then, on September 29th, Kolumbo breached the surface and exploded. The blast was heard over 100 kilometers away, and it sent superheated currents of gas and debris racing across the water to Santorini. Tragically, about 70 people were killed by toxic gases. The eruption also triggered a massive tsunami, with waves up to 20 meters high. Modern science has shown Kolumbo is far from dormant. Its crater floor is a hotbed of geothermal activity, and a 2023 study found a growing magma chamber beneath it, raising concerns about a future explosive event. For decades, scientists debated whether these two volcanoes were fed by the same plumbing. That all changed during a period of intense geological unrest that began in mid-2024. First, GPS instruments detected Santorini's surface swelling by several centimeters, a classic sign of magma accumulating below. Then, on January 27, 2025, the situation escalated. A massive earthquake swarm began, with over 200 tremors rattling the region in just a few weeks. Crucially, the epicenter of this swarm wasn't stationary. It started under Santorini and migrated northeastward, directly towards Kolumbo. This suggested magma wasn't just pooling, it was on the move. The wealth of data from land and ocean bottom sensors, GPS, and satellite radar allowed an international team to reconstruct the events. The story their data told was astonishing. The initial swelling of Santorini was caused by magma filling its shallow reservoir, but the intense earthquake swarm was the sound of that magma breaking out and propagating laterally, forming a dike or a sheet of molten rock. And here's the smoking gun. As the earthquake swarm moved away from Santorini, GPS stations showed that both Santorini and Kolumbo began to deflate simultaneously. It was as if both volcanoes let out a collective sigh. This could only mean one thing: both volcanoes are fed by the same, deeper, magma reservoir. The movement of magma out of this shared source caused a pressure drop felt across the entire system. The two giants, it turns out, compete for the same supply of molten rock. This discovery is not an isolated case. Volcanologists are now identifying similar connections across the globe. In southern Japan, two of the country's most hazardous volcanic centers, the Aira caldera and the Kirishima volcanic group, are separated by just 22 kilometers. Aira is home to the relentlessly active Sakurajima volcano, For years, scientists observed Aira's ground steadily inflating. But during a 2011 eruption of its neighbor, Kirishima, they noticed something peculiar. As Kirishima erupted, Aira's inflation stopped and reversed. The caldera began to deflate. Once Kirishima's eruption ceased, Aira resumed its steady swelling. The only plausible explanation was that magma was being withdrawn from the Aira system to feed the eruption at Kirishima. It was the first clear evidence of a deep subterranean connection, proving that an eruption at one volcano can effectively steal magma from the other. The scale gets even larger in North America. The Cascade volcanic arc stretches over 100 kilometers from California to British Columbia, containing famous peaks like Mount Rainier and Mount St. Helens. For a long time, these were studied as individual threats. But recent research has shattered this illusion. Using geophysical techniques that map the Earth's electrical conductivity, scientists found a large zone of partial melt in the crust between Mount St. Helens, Mount Adams, and Mount Rainier. This anomaly, called the Southern Washington Cascades Conductor, was interpreted as a massive, shared crustal magma reservoir. More advanced seismic imaging has added stunning detail. A 2025 study showed that large magma reservoirs are persistent features beneath most Cascade volcanoes, even dormant ones. And a 2023 study imaged two distinct, deep crustal magma reservoirs running subparallel to each other. One appears to connect Mount Rainier to Mount Adams, while the other connects Mount St. Helens to Mount Hood. This is the scientific basis for the claims of a magma highway beneath the Cascades. While not a literal tunnel, this network allows for the potential transfer of magma and stress across significant distances, linking the fates of multiple volcanoes. So, how do scientists see these unseen connections? One of the most powerful tools is seismic tomography. Just as a CT scan uses X-rays to image a body, seismic tomography uses earthquake waves to create a 3D map of the Earth's interior. These waves slow down when they pass through hotter, molten rock. By deploying a network of seismometers and analyzing delays in wave arrival times, scientists can identify slow zones that correspond to magma reservoirs. While seismic methods reveal the structure, another field called geodesy measures its activity. Geodesy is the science of measuring changes in the Earth's shape. As magma moves, the ground above it swells or subsides. Ultra-precise GPS stations can measure these movements down to the millimeter. At the same time, satellite radar, or INSAR, can create detailed maps of ground deformation over vast areas. This was key in the Santorini study. The true power comes from integrating these datasets. The seismic data tracked the moving magma, while the geodetic data measured the volcano's breathing in response. Together, they told a cohesive story of a shared system being activated. This new understanding that volcanoes are interconnected fundamentally changes our assessment of risk. For decades, volcano forecasting focused on tracking unrest at an individual volcano. But now, that model is too simple. Unrest at one volcano may no longer be a clear indicator of its own eruption. As we saw in Japan, it could be relieved as a neighbor erupts. Conversely, an injection of magma into a shared system could increase pressure on multiple volcanoes at once, a major concern in the Cascades. This complexity makes eruption forecasting much harder. Hazard maps, which delineate areas at risk from lava or ash, may also need to be redrawn. If magma can travel kilometers underground and erupt from a new vent far from the main cone, communities previously considered safe might be at risk. The only way to navigate this new reality is through enhanced, integrated monitoring. We need to expand seismic and geodetic networks to cover entire volcanic regions, not just single peaks. We need offshore observatories to watch submarine volcanoes like Kolumbo. And we need to use tools like AI to rapidly process and interpret the vast amounts of data. The discovery of these subterranean links marks a new chapter in our understanding of Earth. It reveals a planet far more interconnected than we imagined. The ground beneath our feet is a complex web of hidden pathways and simmering reservoirs. These journeys into the fiery underworlds of Greece, Japan, and North America have shown that volcanoes have secret lives and hidden conversations. This deeper understanding brings a heavy responsibility. As our scientific vision sharpens, so does our awareness of the hazards. Living in the shadow of these interconnected giants requires a new level of vigilance and a commitment to listening to the pulse of our living planet.